Well, hi again, welcome to my latest video. Well, since my creator build is somewhat on hold now because of the Intel issue, and even though the BIOS has been released for the motherboard that I happen to have in that system, it's still only a beta BIOS, so I'm not going to upgrade that until I see the final version of it. Anyway, with that, I'm going to start a new series, one that I've been meaning to do for quite a while. It is basically electronics and building electronic circuits and understanding how those circuits work and why they work. In this first one, I want to introduce something new that I just got. Actually, I got a few things. The first thing is I've got two of these. These are power supplies. Now, even though I have that kit that I've built, it was from scratch actually, that I've shown in previous videos, as I'll show here right now, well, it has its limitations. The voltages are pretty much fixed and I can't really adjust it well, whereas this one here will go from up to 50 volts, but variable in both terms of voltage and current, which is very handy when you're trying to build circuits of different types and of unknown characteristics for the parts that are being used. I actually got two of these at an amazing price. That way I can have two different voltages being shown at the same time. And we'll see how that goes. I haven't really used these yet. As a matter of fact, you'll see right here, I still have not done the tear yet on uncovering the little LCD panel that these things have. But I'll do that at the end of this video. Okay? In addition to that, oh, by the way, these come with a set of connectors. So it's got banana plugs on one side, positive and negative, and it's got alligator clips on the other. So they can be adjusted for just about anything that you need to adjust them for. And of course they come with a nice power cable, 120 volts. And I went ahead and purchased some additional stuff as well. First of all, for this, I went and bought two other sets of connectors, power connectors. These actually have 5 different color connectors in them. So it's not just a red and black, but there's a blue and a green and a yellow. So I can actually use these to generate different outputs of different voltages and be able to identify the actual connectors. So from one of these power supplies, if I use it, I'll stick to the standard red and black. On the other one, I may do green and yellow or something similar to that. So that's very handy. It does have an amazing manual. It's one of the few that I've actually appreciated well. It is easy to read. It is fairly detailed in terms of what's covered in it. So it's a big plus that it has a good manual like this that comes with the units. Okay? But in addition to that, I also bought this experimental board. Now this thing has what looks like 4 different panels of plug-in test connectors for building circuits on. And I will describe this in much more detail as I'm about to use it for those of you who have never used one of these. I mean, I was using them in my undergraduate degree to build the circuits for electronic class in electrical engineering. And everybody has them, and we actually had to buy our own so that, these are easy to destroy. So if you were going to destroy it, they didn't want you to destroy the one that is owned by the school. But this came with a lot of stuff. It came with a kit of jumpers. I didn't even open it up yet. Different sizes, different colors, and just a bundle of longer connectors, which are more common. I have a lot of these already from my other experimenter kit that I built. And these are the actual power lugs that you can put at the top of this experimenter panel. This is nice metal, aluminum, painted black, really strong, rigid, so there's no way that it's gonna, get bent out of shape in any way while I'm trying to do anything. And several other things that came with it. There's feet I'm gonna put on there, little rubber feet, and it came with a screwdriver and a little open-end wrench in order to connect up the power connectors to it. And in this packet they have, black, red of course, but there's also a blue and a green. It would have been nice if the blue was actually a yellow, because I usually consider the yellow the opposite of the green when I'm trying to set up a second voltage. But we'll see, maybe I can get some of these separately at some point to match what I wanted. And I may actually, let me see, could I? Yeah, I could actually drill another hole in here if I wanted to put it, if I can go ahead and get one of those. There's plenty of room for it. Okay, so let me put that aside. Now, this is brand new stuff that I just got for this new series. But as you will see, as the series progresses, you'll be seeing some of the other test equipment that's still in the box. And I showed this during a live stream recently, and I think I may have even shown at least one of them in another video as an example of other equipment that I had, but I just haven't used it yet. But in addition to that, I got 2 meters here for today's experiment, which is not going to be a complicated one, just something to get started. But I got my original DVM meter. It sort of tries to mimic a Fluke with the coloring of it and the types of probe connectors it has, and even the stand that it stands up with. But, you know, it's not a Fluke, and it's nowhere near as accurate as one. But in addition to that, as I've shown in a separate review video, I actually have my Fluke 15B. Low cost, low functions. It doesn't have all of the functions that the higher end ones, but more than enough. And I'm going to use these initially to make sure that these voltages that are coming out of these power supplies seems proper. And I'll use both meters to test it so I can compare the two. And then I'll use those as well when we're actually showing the circuit that I want to show. No hints right now. You'll see when I get to it what circuit I'm going to build on this breadboard, and we'll see what happens. So with that, let's get started, okay? Okay, let's start by checking out the accuracy of these power supplies against both of my DVMs. The one on the left is my older one. Like I said, it's an imitation Fluke, nowhere near as accurate, or at least in terms of the specs on it. And over here is my Fluke. A low-end Fluke, but seems to be very accurate from all the tests I've done so far. Let me turn on the 2 power supplies. I was playing with them before so you can see the voltages and currents that I set. They came out of the box set for 30 volts and 5 amps. And I just adjusted them accordingly. And which is what I'm going to do now is I show you how this works. Right now, it does not output this. If I turn, I'll put a meter on each one of these. If I put a meter on this one, I put the meter on this one. Turn them on. Put the backlights on. What you see there is just a little bit of drift current, which is one of the review things on these particular power supplies. They tend to drift a little bit, so I will we'll have to just account for that. But it seems like it still works okay. So if I turn this one on, by hitting this button here, it'll output that voltage and current. So that's set for 10, and right there we have 9.99. This one here is set for 22. Let me put the output. Set for 22, and it's got 22.01. If I lower the voltage down, let's jump down to 10. We can see that it's 10.00. If we lower this one here, we'll bring this one up to 20. I'll just put it at 22. And you see we have 21.99. Okay, so they're both pretty accurate, except overall, when I did my testing, this one here is much more accurate than this one, but they're still pretty good. But both power supplies match up, which is what I did earlier on my own, just to make sure that using the same meter, they showed the same thing. And if I go ahead and switch to probes, you'd see what I mean. So now that one says 9.99, that says 2202. That's 2201 now. When I do the actual experiment as part of this video, the main part of it, you'll see the current being shown when I have it mapped as current reading, okay, which I don't have right now. I have to keep turning the backlight on. But if I adjust the voltages, I find it gets inaccurate at the lower ends. So let's go down to what, 2 volts. And over there on the, that one's on the Fluke now. So it's 2 volts and 0.0067. So really close, but not perfect, obviously. The same thing if I change this one down to a low voltage, 2 volts. This one here comes out to a little bit less accurate at 2.009. Okay, so that gives you the idea that this does work, and these 2 meters are pretty close in terms of their ability to put out the voltage that they say they put. As long as I have it this way, let me do the tears on this. Each one of these has a tear. Probably won't notice much different on the camera. Plastic off. And there we go. They're officially part of my electronics lab now. Okay, let's move on to the first experiment, okay? Okay, in this first experiment, I have a single 1000 ohm resistor right here. It has the color code of brown, black, red. If you're interested in resistor color code, I can make a separate video about that. Just let me know in the comments. But for purposes of this one, we're just going to see when I run 3 volts through it, what will happen. So let me turn this on. I have it set for 3 volts, maximum of half an amp, right? This is only a 1/4 watt resistor. I don't want to burn it out necessarily or have it sparking here. So I'm going to keep that rather low. We're going to be way below that anyway for this, and you'll see what I mean in a moment. So let me apply this settings to it. The voltage will now go from the power supply to the resistor. There we go. Well, we have 3 volts, it steadies out, and it shows that we only have 0.002 amps, or just about 2 milliamps. Let's check to see how accurate that is in the next experiment, okay? Up on the screen right now, I'm showing a symbolic schematic of what we have set up. So it shows the actual meter that's on the power supply. It shows the 1000 ohm resistor. And let me show you how the calculations are done on this using Ohm's law, which is current equals voltage divided by resistance. We have current equal to 3 volts over 1000. That's 3 volts at a 1000 ohm resistor. And the resultant current should have been 0.003 or 3 milliamps. It was close. What we have now is basically the same circuit, but I've now put in line with the power supply and the resistor, the 1000 ohms, a meter that's set for amperage. Specifically, it's set for milliamps or thousandths of an amp. So let's see what we get with this. If I turn it on, same limits are set. Let me apply that to the circuit. This thing says we still have 0.002 amps at 3 volts. But now look what this says. This says we have 3 milliamps or 3.04 milliamps to be exact. Now this only has an amperage scale here, so it's kind of hard to be that accurate. The meter is definitely going to be more accurate than that. So that is the true measurement of it, okay? And here is a schematic, the symbolic schematic, showing the exact same thing. And as you can see, the input voltage is 3. The DVM reading is 0.003. I still have it set for milliamps, so it's 3 milliamps just over it. The resistor is the same. Okay, now I have 3 1K resistors in a row. Now since they're in series, that would be 3000 ohms. If they were in parallel, it would divide, so it would be only 1/3 of 1000 or 333. But these are all in series. This is what we call a voltage divider. Let me see, I'm measuring the voltage just across the center resistor. What do we get when I turn power to it? Same limits I had before. Well, nothing's really registering over here in terms of current because it's gotten so low this thing can't even register it. But we see that there's 1 volt across the center resistor because that's what I have the yellow and the green wires connected to. If I move this over to this one over here, now I see 2 volts because we're across 2000. If I, of course, go ahead and do all 3 of them, that'll show 3000, okay? Or 3 volts in this case. In the first 2 cases, it was 1 volt and then 2 volts and now 3 volts. Now for the symbolic schematic of it, it basically shows exactly what I just created, but a little clearer. You have 3 1000 ohm resistors in a series. I have the meter initially across only the center one. The input voltage is still 3 volts, and the DVM should have read, and it did, 1 volt. So that works. Okay, I've changed the circuit a little bit. Instead of having 3 1K resistors, I now have a single 1K and a 3.3K and a 6.8K all in series. So they're uneven at this point. I did that intentionally. Now if you do the math, that's going to be considerably less current at 3 volts. So what I'm going to do is I've already changed it so that the voltage limit is now 10 volts. I'm leaving it still at a half an amp for maximum current. I have the meter set up to check current and it's in line with the circuit. Let's see what we get. When I apply the voltage, we get 0.89 of a milliamp. If I change it to microamps, we get 899. Okay, so it's considerably less, the current that's flowing through there right now. Now, if you look at the symbolic schematic that I put up, you'll see that I have the right input voltage there, 10 volts. I have the 3 resistors, 1000, 3.3 thousand, and 6.8 thousand ohms in a row. If you do the math with the Ohm's law, that should come out to 0.901 milliamps, or about 901 microamps. So as you can see, we actually are pretty close. It's just a small fraction, a couple of microamps off. Otherwise, it pans out. Okay, now I've changed the circuits. I've now put the meter measuring the voltage across the center resistor. That is the 3.3K or 3300 ohm resistor. Let's see what we get when we apply the voltage. Same limits, 10 volts. And there we go. We got approximately 2.96 volts across that center resistor. If I moved it around to the other resistors, you would see different values because it's dividing the voltage up. If I move this, for example, to the back, so we're across the left 2 resistors, now it's up to 3.85. So anyway, that's how a voltage divider works. Now if we put the symbolic diagram up on the screen, you can see that it's exactly as we calculated. Looking at the voltage for this circuit across the center resistor to 3.3K, it in fact is the value of 2.973 volts. We got very close to that. Okay, so with that, looking ahead in the next video, I'm going to try some different circuits for you, and we'll see how that pans out. Okay, before I move on to later episodes in this new series, I want to cover a few concepts in electrical and electrical engineering. The first one, which is key, is called Ohm's law. I talked about it during this video, and the basic formula is pretty simple. The voltage equals the current times resistance. And then through algebra, you can convert that to how to get current, which is voltage over resistance, and resistance itself, which is voltage over current. Also, I want to cover some resolution notations that I mentioned. First off, when you're making something much larger than it is in multiples, kilo represents 1,000 times the original value, or thousandths. Mega represents 1 million times, or millions. Giga represents 1 billion times, or billions. Tera represents 1 trillion times, or trillions. Then when you go in the other direction, making things extremely small, then you have something called milli, which represents 1,000th or thousandths. And then micro, which represents 1 million or millions. Pica representing 1 billionth or billionths. And nano represents 1 trillionth or trillionths. Anyway, I do appreciate everybody watching this video today, and I look forward to taking a look at some of my future episodes. Take care.